Okay. Yeah, thank you. Thank you for this opportunity to give a presentation at the summer school for data science for Earth observation. My name is Ralf Kohlhaas. I'm the section head of the optics section at SRON, Space Research Organization Netherlands. And I'm going to talk, well, a big class of instruments which actually bring you the data which you're using for your daily work, which are passive optical instruments. So what I'm going to do in this presentation, I will at first give my personal definition. What are those passive instruments and why do I find them important? Then I will talk about several examples and types of those spectral images. Then I will talk about spectropolarimeters and then about the topic of calibration. Why is that important for those instruments? And then I will give some personal speculation. Why or how could those instruments look like in the future? Okay, let's go at first to the definition for this talk. So it's quite simple. What do I call a passive instrument is we just use the sun as a light source. So for example, the sun gets reflected by the Earth. The light travels through the atmosphere, and from the light collected by a passive instrument, we can infer some information, for example, on the land or on the atmosphere. What I'm going to call optical in this talk is I will basically call it from the UV range to the infrared range. So why are those instruments important? And it's nice for that to look maybe at the map of the ESA Earth fleet. So it's basically divided in big three parts. You have the science missions, the Copernicus program from the EU, and you have meteorology. So for example, in the science part, in the future, you have interesting things like the FLEX, which is going to measure photosynthesis from space, or you have PROOFs, which is basically a metrology standard for all other instruments you will have. Then you have the Copernicus program, which contains, for example, Sentinel-2. Many of you might use data from this from the land imager instrument. And meteorology, well, that's, for example, for weather. So it's a very large number of satellites which are already in space and are coming. And now I did this task and I was just darkening everything, which is not carrying a passive optical instrument. So let's hope I didn't make too many mistakes. So I darkened everything out. And so what you see is that I didn't darken out so much. So there's a lot of instruments left. So actually, it's about like 60% of our satellites, they carry passive optical instruments. So it's the dominating group of instruments. And that's not only the case for ESA, that's also, for example, for the other space agencies like JAXA and NASA, and also for private endeavors about this ratio. So it's the dominating type of instruments, and this means it's those are the crucial tools for monitoring the land, the oceans, or for example, the atmosphere, well, all those applications you are working on. Now, I would like to go into the biggest group of instruments, which are spectral imagers. So that's everything which gives you both a spectrum and an image on the ground. And there are three big types. So one is bandpass imagers, one is dispersive spectrometers, and then we have Fourier transform spectrometers. And most other instrument types, there are variations of those. And there are a few more niche cases. I will not talk about them, but usually you will hit one of those three. So let's go into the first one, which are bandpass filter instruments. So what is this? Usually you put some spectral filters, there can be some color filters, somewhere in your instrument. Very often you put them on your detector. And then if you put them on the detector, then it's very similar as it works in your mobile phone. You have a lens, you have a sensor, which you see here on the right. And your image is seen on your sensor. Now, if we have stripes on the detector, this is how we usually do it, is we can take a spot on the ground, which you see here in white, and then if the satellite is moving, a lot of our satellites are in low Earth orbit, then the same spot on the ground is seen by different filters. So we're doing this scanning operation, which you can call either push boom or maybe push frame for those snapshot images. All right, let's go into some examples of those instruments. So the first one is Landsat 8. So quite some of you might be using Landsat 8 or Landsat 9 data. And I was quite impressed when I was looking up this image from how the focal plane looks like. Like very often when we think about, oh, I would like to build a satellite instrument, what can we do? Then you start, oh, let's start with some detector. That's what we can afford. And actually what they did is they took 14 detectors. That's what you see here. So that's in the image plane of the instrument, and they interleaved them. So you have a lot of detectors, and on each of them there are those bandpass filters, like from the previous slide, right? And what this gives you is that you have a lot of pixels in this direction. So this means that even with a quite small count sampling of 30 meters, we can have a wide swath. So that's very important. For Landsat 8, it has 9 bands. It has a fairly big spectral range of 0.4 to 2.3 micrometers, and the spectral resolution, which spans from 20 nanometers to 200 nanometers, depends a bit on where you are. Usually the spectral resolutions at the lower wavelengths, they're a bit better. And the signal-to-noise ratio is quite solid, between 80 to 300. So this design of the focal plane, you see it also, for example, for Landsat 9, which was launched in 2021, and for Sentinel-2, it's actually built in the same way. It's the prevailing way of building those big instruments. Then let's look at an instrument which will come in the future, which is will be launched, for example, in Q4 of this year, which is Hyperlight with the CS Simba instrument. What this does, it only uses one detector. It's quite a nice design from IMEC, Belgium Institute. They put the filter straight on the detector. And it will be in a private partnership with ESA and the Belgian space agencies. Will there be a satellite with about the 12U volume, and it will have a swath of about like 80 kilometers and still quite a good spatial resolution of 20 meters and much more bands, so 150 bands, so much better spectral resolution. Though it is only, if you compare it to Landsat or Sentinel-2, it's only in the visible range. SNR will be 120. Here in the middle, you have an example how the detector chip looks like, and on the right-hand side, you see how the optomechanics look like. Often what we do is we take just 3 mirrors, so we call it 3 mirror anastigmat, and then the detector, so you get a nice non-aberrated image on the detector. So a good image for the data for you to use. All right. Now, let's go into dispersive spectrometers, which is the second biggest group for passive imaging instruments. So, well, I think most of you have seen some form of spectrometer. So it is quite simple. You take a few mirrors, you have a slit in your system, and then you re-image the slit over a grating on the detector. So the grating splits the light in different colors, and you get in one direction different colors. So now what you see immediately is that, well, in one direction you don't have spatial information because you have your spectral information. So all you can do is to scan with a stripe over the ground. So that's what we do. So for example, in this case, we would move in this direction in order to scan over the ground. We call this push boom imaging. Now let's go into some examples. So one example is, for example, Sentinel-5. This was launched about now 3 weeks ago. It carries several grating spectrometers, 5 of them, from the visible range to the shortwave infrared range. And in this image, I show you the shortwave infrared spectrometer, which well, so there's no telescope here, right? So it's straight to slit, and from the slit, the light is split here. I think it's not working in 2 paths over dichroic mirrors, and then you have 2 channels. One is the sphere 1 channel, and the other one is the sphere 3 channel. What is interesting about this instrument is that it has a very special grating called an immerse grating, which was delivered by SRON. What it does is that the light at first goes through a medium with a high refractive index, which allowed to use a smaller grating, which allowed that the size of the instrument was not so big. And so then after the grating, it just goes on a lens system and the light is imaged on the detector. What are the parameters of this instrument? It has a swath of 2,700 kilometers, so very large. A spatial resolution of 7 kilometers. So if you compare this, for example, before to Landsat with the 30 meters, much larger. A spectral range here in the shortwave infrared, so around 1600 nanometer, and in the shortwave infrared 3 range, 2300 to 2400 nanometer. But it has a much better spectral resolution. So the spectral resolution about 0.2 nanometer. So that's much better than if you compare to the 30 or 60 or 20 nanometer for the bandpass images. SNR is still quite solid. So there's a SNR of 250 in the Sphere 1 range and 120 in the Sphere 3 range. Let's go to another example of an imaging spectrometer. So that's ENMAP, flies around since 2022, stands for Environmental Mapping and Analysis Program. And so it doesn't use a grating. Very often use gratings. In this case, it is not the case. It uses some interestingly shaped curved prisms. Yeah, so everybody of you knows a prism. You can use a prism to split light, right? And in this case, they make it curved so that it corrects like aberrations, image distortions. So that's why it has this weird shape. It has the instrument has a swath of 30 kilometers. A sampling of 30 meters, and a spectral range which covers the full visible range to the shortwave infrared, so 420 to 2450 nanometer. Still quite a good spectral resolution, 6 nanometer in the visible and 10 nanometer in the shortwave infrared, and quite okay signal-to-noise ratio with 400 in the visible and 180 in the shortwave infrared. What you see though is quite small swath, right? And I showed before like Landsat with the 180, that's only 30 kilometers, so it's quite a bit less. It has though a better spectral resolution. All right, so that's again same principle, right? So you have a slit, some spectrometer, you go on the detector. In this case, it is curved prisms instead of rotating. Then I would like to highlight an instrument which will come in the future, which is SHIME. So that's from the European Space Agency. It stands for Copernicus Hyperspectral Imaging Mission for the Environment. Hopefully planned to be launched in 2028, but things usually delay. What is interesting about this one is that it takes one telescope and then it goes on 3 slits. And those slits, I try to draw this here in a staggered way. So you go in 3 spectrometers at the same time, and this is to make to have a bigger swath, basically. It's the same trick as you have seen it before with the Landsat data, with those staggered detectors. Now they stagger those slits, and then they build 3 spectrometers. It has a swath of 130 kilometers, a sampling of 30 meters, big spectral range, spectral resolution of 10 nanometer, and it's supposed to have a very high signal-to-noise ratio. So I think it will be a very nice instrument. Will still take some time before you have all the free data, but that's how it's going to look like. So there's so for the instrument, there's a slit. A mirror, a curve grating, which disperses the light, another mirror, and then it focuses on a detector. Yes, so I mean, those type of instruments like the spectrometer type, you see it very often. For example, last year you had from Planet Tanager, I hope I pronounced it correctly. It's a similar instrument. It is already flying. It has though a smaller swath. So does, for example, not do this trick with the staggered slits. All right, then let's go to the third category, which are Fourier transform spectrometers. Yeah, I think most of you have heard about how a Fourier transform spectrometer works, or at least a Michelson interferometer. So what you do is you take a telescope, you get at the end the collimated beam, and then you have two beam paths, and depending on the path length difference between for example, the upper path and the lower path, you get destructive or a constructive interference. And now let's say we are going to move the mirror. Then what we can do is with the incidence spectrum is basically doing a Fourier transform. And so if we take the data, then doing Fourier transform gives you the incidence spectrum. Very often those instruments, they actually don't show you a stripe like in the grating spectrometers or in the bandpass imagers where you have the full field, but they often only point at a spot on the ground, or maybe they go on the limb, and so you only have a few spots actually. I have for that only one example for this type of instrument, which is EASI Next Generation, which was as well launched only a few weeks ago from CNES and ESA. So I will not go into the full design of this instrument, but what is interesting about it, so it's very similar layout as I had on my previous slide. So you have some telescope, a field stop, you collimate a beam. So this you see again here. What is different though is that in order to have a good field of view, they use some prisms which basically glide into each other to get a variable a plate with a variable thickness. This makes that the field of view can be a bit bigger. What is nice about it, it's basically goes in unison with the movement of the mirror and the movement of the prisms. So that's quite a complex mechanism, actually, an active mechanism. It has the instrument has quite a big swath from 2,000 kilometer. Spatial resolution is 12 kilometer. You see a bit back. So you, very often for those applications that, for example, look at atmospheric composition, often they have maybe a bit better spectral resolution, but the spatial resolution is not so good, right? And then though it has a quite big spectral range, so 3.6 to 15 micrometer and mid-wave to thermal infrared. And quite a solid spectral resolution from 0.3 nanometer to about 6 nanometer, and also quite good signal to noise ratio from 200 to 2000. Maybe something interesting about it in addition is what it does here. It has 4 spots. So what it does is you have 4 dots on the ground. That's what you're imaging. And then you have a scan mechanism. And with a scan mechanism, it just moves one spot. And it's like a whisk broom type of instrument. Moves around to get an image on the ground. Okay, so I've shown now 3 types, like the dispersive spectrometer, bandpass imager, and Fourier transform spectrometer. And when I was putting those slides together, I was actually wondering, okay, why do we use those different types at all? And I was especially wondering about, for the case of the dispersive spectrometer versus the bandpass imager. So if you think about, if you want to get a new instrument, the question you have to ask yourself, especially, is how much light you collect, and that's basically determined by 2 main things, which is your étendue of your system and how much transmission you have. For example, if you reject a lot of light. So I've written down here an easy formula, which is basically what's the power. The power you get from an instrument is the reflected sun radiance times the étendue times the effective transmission. What is the radiance, which is basically this here. It's an area times a solid angle. And so what we are asking ourselves is, with the étendue, is how much I can collect from this cone. So this is basically determined by how big the aperture of your system is, and what is the size of the area. So I want to get a big area, and I want to get a big cone, which means big aperture. But also, I don't want to throw a lot of light away like you do it in the bandpass imager. So if I now look a little bit further, then it's like this. There's only a limited number of choices we have for detectors, space qualified detectors. Usually we choose a detector, and that usually almost approximately fixes your aperture. And then if I compare bandpass imager against the grating spectrometer, then what you see, you could say, well, it's much better bandpass imager because it images a big area on ground, while the dispersive spectrometer only scans the stripe. But the bandpass imager rejects a lot of light because, well, it just lets, for example, 2 nanometers through over 400 nanometer range, so a lot of light is just thrown away. So that's bad. And so if you look at it a little bit more, how it actually is that if you have approximately as many long track pixels as spectral channels, then the same perform on paper approximately equal. And if you have much more pixels than channels, then the bandpass imager is almost always better. And that's what you also see back. So for low spectral resolutions, with quite some pixels, you choose the bandpass imager. But I'm saying here as well that in most cases, the bandpass imager would be good as well. So why do we ever build a dispersive spectrometer? It doesn't seem even like a good idea because it's very easy. I just put some filters on the detector, I have some mirrors, done, right? And we build all our instruments like this. So then if you look into that, why we are not doing that, then of course some engineering reasons. There's some stuff we can not do so well. And so for example, one of them is that if you look at those filters, they are made of thin film interference filters. If I go at them at a different angle than straight, then the position of the filter will shift. And this means if I go with a focusing beam, it will broaden the response of the filter. This means that, for example, at 2.3 micrometer, let's say 2.3 micrometer, we would like to make a spectrometer with 0.2 nanometer. That's very hard because if I have an f/2 system, so big aperture versus a focal length, then I would broaden this to 25 nanometer. It doesn't work. Another engineering reason is that it's just hard to put a lot of filters over a wide spectral range. And that's also the reason I showed you before instruments like Scheim and Tanager, that those instruments are still built with dispersive components. Okay, now we have treated spectral imaging instruments. Let's go into spectropolarimeters. So for that, we can use very similar instruments I've just shown, and we just make it now more complicated. So what we do is we add some polarization sensitivity. And so how can you do that? For example, what you can do is, so the electric field is polarized. And so what you can do is you take a polarizer, which you rotate, for example, and then you measure the transmitted light through this polarizer. What you can also do is you take a polarization beam splitter. So you split the incident light according to polarization. Then you can analyze the incident polarization. And you can also put just a lot of polarizers on the detector straight. So not only that you put some bandpass filters, but also some polarization sensitive pixels. And there's another option, which is channeled or spectral modulation. This goes straight on my next slide. So that's immediately an example, which is SPEX1 instrument where we had quite some contributions. Was launched in February this year. What it does is it's a multi-angle instrument, and we use it to measure aerosols in the atmosphere. And it's basically a spectrometer plus some spectral modulation close to the slit of the instrument. And it uses some wave plates, I will not go into the details, and multi-order retarders in order to encode the polarization in the spectrum. But it basically does is what we see on the detector is a nice stripe pattern. So if you have a high polarization, then what we will have is that we have this different stripes. And low polarization will mean that it's quite continuous. Swath is 100 kilometers. There's a 5 viewing angles, spatial resolution of 5 kilometers. What is very important for those kind of instruments is how well can I measure the polarization. So that's the polarimetric position. And it is worked in the visible spectral range, which is most useful for measuring aerosols. Has a spectral resolution of around 20 nanometers. And if you're interested in more how to use those data, especially how to use polarimetric data, there will be tomorrow a hands-on tutorial from Jeroen Ritjens and Laura van der Straat. Then another instrument example, which is 3MI from ESA, was also launched a few weeks ago. It's a multi-angle spectropolarimeter with much more views. What it does is it takes a filter wheel. So you see here a wheel of different filters, and then you basically look on the ground and just spins, and you look through those filters. And then because those filters are also have polarization filters in there, you can measure, both spectral and polarization information. It has a very big swath, 2,200 kilometers, also much bigger instrument. The Specs 1 is like this is the size like that. 4 kilometer spatial resolution. Polarimetric precision requirements 0.5%. We don't know yet where they are because it was just launched. Spectral range though goes up to the shortwave infrared, which is very nice, for example, for detection over snow, where polarimetric and basically the light reflection makes that you can detect less good. Okay, so then at 12 bands, polarimetric spectral resolution over 20 nanometers. So that's 3MI. And then you have CO2M map. So that's for the upcoming CO2M mission from the European Space Agency, also multi-angle polarimeter. What it does is works very similar to the bandpass images, but it adds on the detector polarization filters. So what you see is here in this little insert, there are small polarization filters. You take 3 of them, 0 degrees, 60 degrees, 120 degrees. From that you can get the polarization, and from the bandpass filters, well, you get the color. Then you have 6 of those channels, and then you superimpose them with the micropolarizers. And a lot of viewing angles, and polarimetric spectral resolution of 20 nanometer. Hopefully to be launched end of next year. Well, okay. Now I go on to the topic of the importance of calibration. So you have seen, I've just rushed through a lot of instruments and examples, right? And so what is almost equally important as building a good instrument is also calibrating it very well. So, because usually we build something, and of course we try to build a perfect instrument and so on, but we don't manage, right? And then we need to calibrate it, we need to measure it. And so usually our requirement is that we need to calibrate it 3 times better than our tolerance. And it should be also for a representative scene. So that's also a very important one, because a lot of people do shortcuts here. For example, you say, oh, my instrument works perfectly if my scene is homogeneous. You get it in space, and then you suddenly see there are lots of errors and nobody knows why. Examples of things which have to be calibrated is, for example, the spectral line within the positions. That's in the case of a spectrometer. Radiometry is you would like to be sure that you know exactly how much light you're getting into your instrument, and any kind of offsets in your detector. Let's go into 2 examples of calibration. So one is on stray light. That's especially important for dispersal spectrometers. So what you can have in your system is, for example, that your mirrors have some roughness, or that your gratings are not perfect, and then you will get, for example, on the detector all kinds of additional peaks or ghosts, or you will get that the light intensity on your detector rolls off. So where you would like to have a straight peak, you don't have it. And what you have to do is you have to measure the spray light with a very, very high contrast. So often we try at least 7 orders of magnitude or better in order to be able to well, at first know how much it is, but then also to correct for it. For example, this can give you after correction factors up to a factor 10. So for example, here you see some kernels, you see a lot of stray light in this direction for one position, for one wavelength. Here another position, they also look different, so it's quite complicated to model and then to correct. So a lot of work goes into that. Then I have another example, which are signal-dependent offsets. Yeah, we all like to model a detector as like something like this that is perfectly a linear system without the offset or anything. So you get your light intensity, you have more light or perfectly linear response, right? In reality, they don't work like this at all. They make a lot of errors. And actually, quite a bad one is if it depends on your distribution of your light on your detector. And this is, for example, something we have seen recently for this instrument we have just launched, Specs 1. So we compared for example, if you compare on this graph, on the x-axis the radiance, how much light you have, on the y-axis is the comparison between the ocean imager, which is on pace, and the Specs 1 instrument, and that you see for some detector settings, there were big errors. And luckily we could correct that with just finding the right settings on the detector, but got a bit lucky because we had to copy after that in the lab. We also tried, for example, we drawn lots of people onto the project to fix this problem. For example, to just model it, to do all kinds of this complex distribution of light in the detector, model and correct it, but it didn't work as well. So there needs to be go a lot of effort into this, because else, well, this is a representative detector, right? So if you look at the data, they're actually wrong. So if you look at, for example, low intensity, this is incorrect data. Okay. Then on the speculation about the future, so I have the 2 slides, I think, 3 slides. So there are some trends which are already happening, so they're obvious. I almost don't have to speculate about this. For example, let's say that we will have more constellations of satellites. For example, Planet has something like 200 operational satellites, GHZ-sat. So we are more coming from the science side for atmospheric composition. They have something like 12 instruments right now in space. So I think this will become even more. Then we also start to step, if you look at those instruments which cycle around the Earth, which are not in geostationary orbit, they start to go a little bit lower. So we try to go to a little bit very low Earth orbit, which makes it we can use less big apertures for the same amount of light. And even lower would be those high altitude platforms. So it looks a bit like sci-fi, but they're actually flying around. And for that, you need very small, compact optical instrument to be able to put them on them. Then something which we already see as well, because we have problems with the data rates, is to do a lot of onboard processing to do onboard already reduce the data volume. And what I can also imagine is what we will see more is, for example, is to have actively responding systems. For example, you have one system which looks a little bit forward, says, oh, there's something interesting. And then the next sensor on the same platform says, oh, let's look over there. Or on a satellite just going after. What about the optical payloads? So one thing which I also realized also when putting the slides together was the systems, they don't scale well at the end. So if you think about it, if you want to make better spectrometers or get much more light and so on, it becomes really big, the satellites. So what I could imagine what happens is that we will do things like in this example, here's a mock-up of Plato. So Plato is an astronomical mission. We calibrated SRON a few of those cameras, that we might just put lots of cameras or detectors with their own detector on the same platform. This is something to maybe scale better our instruments. And so something else. So now this comes bit more towards the future, is to make our instruments, of course, much more complicated, but hopefully also better. So, for example, one thing is to use nano structured elements, so they can give you an interesting response, so they can give you they can be smaller or more lightweight for the same system performance, and but to, from the start, integrate everything, so that you integrate, that you design both your retrieval algorithm and your system at the same time, and actually at the end you cannot disentangle them anymore. So you will not have anymore, as you may like it right now, that you just get a grid of some spectral data. You don't have that. It will not, in case of those instruments, it will not be there. So there you will get straight out of the system, for example, a gas concentration. Something we have been working on is to put the photonic crystal filters on the detector. So that's a fancy painting of this. So this little holes in, for example, silicon, periodic holes. And what it does, it gives a very complicated spectral response of the filters. But if we select them right, so we use evolutionary algorithms, then you take a radiant spectrum, you multiply times your filters, you get different intensities, but since you have a lot of information of the position of the lines from the start, from your radiance model, and you know how the filters look like, you can reconstruct the spectrum, or you can straight fit your atmosphere model to the filters, and then you immediately can get the gas concentration. So in this case, you never have a spectrum. Another thing which I think might happen, but that's really completely pure speculation from my side now. Something which I like is in the field of optics, you have a thing since a few years which is called diffractive neural network. Everybody works, I guess most of you work with neural networks. Quite a standard tool right now in data science, but we can also move the operation on the optical side. So we can make diffractive elements which copy them. So your layers are then diffractive optical elements. And so then from the start, we would, in a hybrid way, design both the network and the diffractive part in order to get, for example, again, the gas concentration or some other target. The other thing is, big thing in the field of optics and photonics is integrated photonics. So basically you have those small chips, you have a fiber, you go into this chip, and for example, you can also build a spectrometer there. So I find this quite interesting because of its potential scalability. So you take a few chips and then you just build 4 million of those, and then you put it on your satellites. Simplified. But what I think is hard about this is the question: how do you couple your light from your aperture into your system, and how do you make that the losses are not so big? So I think this will be a main challenge for that. All right, and with that, I'm already at the end of the presentation. So I've shown you a lot of different types of instruments. The main types are bandpass imagers, dispersive spectrometers, Fourier transform spectrometers. Quickly pointed out how important calibration is for the data and the reliability of the data, and I gave a little bit of a speculation about the future, but the main message is that I think, well, actually, that I believe if you're going to build instruments differently, what you're going to do is you need the qualifications of both being good at retrievals and data science and understanding the instruments, or at least having teams which are closely working together. So that's about the future. Okay, that's it. So thank you.